Friends, in the last session towards the end we started looking at some design aspects and particularly an example of sodium thiosulfate oxidation in a stirred tank reactor, an adiabatic operation in which we saw we get multiple steady states. Same stirred tank reactor, even if we are not doing an adiabatic operation, but let us say we are trying to do an isothermal operation, then we can see in this next example the following behavior. What we are seeing on the right hand side, essentially what we have is a stirred tank reactor. So, we have a stirred tank reactor and it is a continuous operation and there is some cooling that is taking place, so that the temperature is controlled. Now, what we are seeing results over here are what happens when you change the coolant flow rate and what steady state temperature. So, steady state temperature in the reactor on the y axis. So, let us try to do an experiment where let us say that we start with very high value of coolant flow rate. Now, when you have very high value of coolant flow rate, you can expect the temperatures to be lower and this is what we get. So, let us now do an experiment where we started with this point and then went on decreasing the flow rate, wait for some time for steady state to attain and note the temperature, and this is what we will see if we keep on decreasing the coolant flow rate. If we start the experiment other way round, that we keep very low coolant flow rate, then we may expect temperatures to be high and this is what we can expect. So, very high temperature and then temperature progressively decreases as we are increasing the coolant flow rate. But if you increase the coolant flow rate beyond certain value, we now actually see a very low temperature, or in other words the same hysteresis effect is seen over here as well. Namely, for increasing the coolant flow rate, we get progressively reducing the temperatures, but at a higher levels of temperatures, and at some point we suddenly see that temperature goes to a low value. It is again an exothermic reaction. So, you expect that temperatures low would mean that very low reaction rates and therefore, very little conversion. So, what we see here is we suddenly go to a lower branch, but now again you start increasing the temperature, we remain at the lower branch increasing the coolant flow rate, we remain on this lower branch and then at some point we suddenly jump to a higher temperature branch. So, then hysteresis effect similar to what we had seen earlier in our adiabatic reactor. And also interesting is that suppose we fix our coolant flow rate at this value 40, then at this coolant flow rate we have multiple steady state possible, number 1, number 2 and number 3. So, question then arises that if you are trying to run a reactor with this value of coolant flow rate, which of these 3 steady states will you get? Will you get high temperature, low temperature or the intermediate temperature? Now, it turns out, and we will look at this behavior little later, that number 2 is inherently unstable. So, if we do not have a controller mechanism, we will never get this number 2. It is called unstable steady state, and only possibilities are 1 and 3. Of course, if you have a controller, then you can artificially make that steady state stable and get those results. So, this is what happens, typically can happen in a stirred tank reactor. Let us take another example of a batch reactor, and there are two examples shown over here. The first example is the methyl nitrate decomposition, methyl nitrate decomposition, and this is a batch reactor. So, what you are seeing on the x axis is the initial temperature, and this is initial pressure. So, on y axis is initial pressure, this is a gas phase reaction. So, initial pressure, and on x axis we have initial temperature. Now, what we see over here is an separatrix. The name for this separatrix will become clear in a minute. That is, in this phase plane of initial pressure versus initial temperature, if your operating conditions are in this region, that is below this line, then you have a safe reaction. There is no reason to worry about. However, if your operating condition is in this particular region above this line, then we have an explosion occurring in our reactor, a disaster. Okay. And the reason why we call this line as separatrix is because we can see that this line divides this phase plane of initial pressure and initial temperature into two different regions, separate them into two different regions, a safe operation and an explosion. Now, one way of looking at such situation is, we say that we obviously do not start with those initial conditions where you have explosion. So, you always design here, but look at how sensitive this behavior is. For example, let me just for sake of illustration, let us say that we have chosen an operating condition over here, okay, a safe operation. I have no cause to be worried, but something happens at the start of this reaction, and temperature which was supposed to have been at these levels, which is about 530 K, incidentally happens to be 540 or 535, same pressure but higher temperature. And now look at what has happened in our reaction. So, this is my new operating condition, and this is now in a danger explosive range. So, a small perturbation out of 500 K or 530 K, 10 is less than 2% error, okay, less than 2% error, but that can have disastrous implication for our reactor operation. On the right is another example where we are looking at hydrogen oxygen mixtures and combustion reactions. these reactions are becoming increasingly important because hydrogen is being looked at as a fuel for the future. But look at what is likely to happen in such reactions. Again, what we have here is initial temperature, that is the startup temperature on x axis, and pressure on y axis, initial pressure on y axis. And once again we have a separatrix which divides this phase plane into two regions of explosion and no explosion. And unlike in the previous example, this separatrix is a crazy shape, it is not a unimodal, it is not continuously going down. What it means is, for example, if we are starting somewhere over here, all these conditions up to this point are safe, but then we have unsafe region in this boundary, and once again we have a safe region, or in other words, this portion safe operation, this portion unsafe operation, once again safe operation. So, slightly different. What it means is, we are looking at partial pressures. So, lower pressures and higher pressures are okay for a given temperature, but any intermediate pressure is a cause for concern, that is, we will have an explosion. So, this is another possible behavior in a batch reactor, and once again the sensitivity issue is also at play, that is, to cause changes from non-explosive to explosive region, you do not need a huge change or operating condition difference. A small difference is enough to cross over the boundary between safe operation to an explosive operation. This is yet another example, and this time we are looking at a tubular reactor, and we are looking at a reaction of vinyl acetate synthesis. Vinyl acetate synthesis in a tubular reactor, and what we are looking at is, on the x axis is the length along the reactor. This is where my reactants are coming in, this is where my products are coming out. So, on x axis I am looking at length, and on y axis I am looking at temperature in the reactor. There are two different operations shown, low temperature and high temperature operations, but we will right now look at a behavior which is of a nature such that if you have a low temperature operation, we are starting with temperature of about 400 K and temperatures remains well below 500 K during the entire reactor. It's about 450 K and so on. But something called high temperature operation, and we will try to analyze this situation in more detail. In a high temperature operation, if you look at this behavior, initially the temperatures are well controlled, but then something happens in our reaction and suddenly the temperature shoots up by about 300 to 400 Kelvin, and once again it comes down. Now, if you look at this behavior of this temperature suddenly increasing, this is a cause for concern. Why? Because if you look at the slope of how rapidly this temperature is increasing. It is too high, it is almost infinitely large, and so is the way in which it is cooling, giving rise to an effect what is called as hot spot in a tubular reactor. If you look at this temperature rise, it is almost like there is a region in the reactor, this particular spot, where temperature is suddenly very high. Let us say that point is somewhere over here. So, below this temperatures are all right, after this presumably temperatures are all right, but there is a hot spot in the reactor at this particular location, and this behavior is like a spot behavior because the slope of this increase in temperature is almost infinitely large. Now, one may argue that temperatures are coming down, so why bother about this? We have to be worried about this behavior for a simple reason. This magnitude what you see here increase is not a small magnitude, it is about 300 K. And just imagine a scenario in which your reactor is made up of a material which can withstand only about 700 K, because you are going to operate it at 500 K or below 500 K. So, you thought to give a safe margin, let us make a reactor which can withstand up to 700 K. And look at what will happen if we have a operation like this. We will have temperatures reaching as high as 800 K, resulting into complete meltdown of this material, because its stability was, or its melting point is only about 700, and then you never know what will happen if the reactor melts. A sure recipe for an accident. It is a matter of little consequence that these temperatures also come down. Now, why do they come down here? They come down here because in this particular, this was a controlled experiment. They come down because by the time temperature reaches to such a high value, your reactant is almost completely exhausted, and therefore, you have reaction almost stopping almost instantaneously. So, no heat generation anymore, and you have a complete meltdown. On the top what you see is a plot in which this is called heat of reaction parameter on x axis, and we will see what that parameter is in a minute, versus cooling parameter. So, heating versus cooling, and again a kind of separatrix where this is my low temperature operation, that is safe operation, this is my high temperature operation or something that I need to avoid. Once again, I will emphasize the fact that transition between this low temperature to high temperature need not occur because of some significant change in any operating condition. A small few percentage point change is enough for this behavior to take form. So, now let us try to understand what is it that is making these operations so sensitive, or in other words, what we have seen so far, this tubular reactor, batch reactor or a stirred tank reactor, three different types of reactors. So, we have covered all the bases, is that a small perturbation in an operating condition can cause significant deviations from the normal operation or steady state system behavior, and such behavior is referred to as parametric sensitivity of a chemical reactor. Now, all these results that you saw are experimental results. So, they were carried out in a well controlled environment, but it is always not very easy to carry out these reactors where you cause an explosion and yet there is no damage. Just imagine how much safety precautions that you will have to do. So, mathematical analysis of the situation comes handy, at least to see what is the reason for this kind of sensitive behavior, and furthermore, are there any operating parameter regimes where we can prevent such behavior. So, we will see that by doing a simple mathematical analysis, and let us try to look at this analysis for plug flow reactor and behavior of hotspot, because if you realize plug flow reactor and batch reactors are equivalent in time and space domains. Space domain for plug flow reactor and time domain for batch reactor, they are equivalent. That comes out mathematically also, because your mass balance equations are almost identical, except we have real time in one case and residence time in other case. So, let us consider a reaction A1 going to A2 in a plug flow reactor, whether it is a catalytic reaction or otherwise. Right now we will not worry about that. Okay. So, for this particular reactor, our mass balance, using our standard notation, we can write U dC1 dz. I am going to assume a simple plug flow reactor, ideal flow and so on, and just say that this reaction is a nth order reaction, So, this is my mass balance. Let us put our energy balance now. We are carrying out an exothermic reaction and we are carrying out by cooling it. So, we can hope that there is a safe operation, but let us see what happens. So, we write the energy balance convective energy transport on the left hand side, the first term on the right hand side representing the heat generation, and heat removal rate. So, what am I writing my balances for? The concentration or the mass balance for species A. So, C1 is the concentration of A1 in the reactor, and energy balance which gives me how temperature will vary T as a result of generation due to reaction and removal due to the coolant which is flowing outside this tube. So, we are removing this heat. The diameter of the tube is dt, U is the overall heat transfer coefficient, and Tr is the reference temperature for the coolant fluid. So, with these two balances, if you look at these balances, there are too many parameters in the system. So, let us try to reduce the parameter space by few, and it turns out that we will end up with 2 if when we do this by looking at defining some dimensionless quantities, starting with x as dimensionless concentration in this manner, which is nothing but our conversion C10, that is the inlet concentration minus the exit concentration divided by inlet concentration. Let me define my dimensionless temperature as T minus T0 divided by T0. Temperature T in the reactor minus what was there at the inlet conditions into gamma. We will worry about what is this gamma. This gamma as E by r T naught and residence time tau as z by velocity u into k at T naught into C10 raised to n minus 1. What is this? All this k T0 C1 raised to n minus 1 and all that. How did we get that? We are going to define this in this manner. So, let us see what we will get, and I will just show few steps and then show the final result. For example, our rate constant k, which is a function of temperature, we can write this as k. We typically write this, for example, as Arrhenius rate law, right. But we can also alternatively write this as, by taking T naught as a reference temperature, let us just rearrangement to serve our purpose, and what is that purpose will become clear in a minute. So, this we can write as k naught, and let us take which in terms of our quantities that we have defined dimensionless temperature. For example, we can write this in the following manner. That is my dimensionless reaction rate or reaction rate rather in terms of this dimensionless temperature. So, now this motivation for making this dimensionless will become clear. For example, if I take my mass balance and instead of C1 express it in terms of x, I will end up with the following, and the appropriate tau. So, all I am going to do is put these dimensionless quantities into these mass balances, and I will get my dimensionless equation of mass balance as with concentration dimensionless concentration x 0 at the inlet. Okay. Now, if I do the same exercise, and this is where little bit of manipulation will come in, that is, take this theta, put it in this energy balance and put all other dimensionless quantities, I get my dimensionless energy balance in the following manner. Let me theta is my dimensionless temperature, tau is my dimensionless residence time. What is my B? My parameter B has minus delta H naught into C10 gamma divided by rho Cp into T naught, and my parameter psi, which is appearing in the second equation, is minus delta H K 0 C10 raised to n by U T naught 4 dt by 4 into gamma. Now, the reason for writing this in this particular manner is now will become clear. You look at this original mass and energy balance. How many parameters did we have there? If you consider U, rho, Cp, delta H, heat transfer coefficient, dT, Tr, N and all Arrhenius rate constants and so on. But look at the behavior in terms of dimensionless quantities. How many parameters do we have in this energy balance and mass balance? We have N and gamma which are reaction related. Okay. B, if you remember something little bit from our previous discussions, is actually nothing but maximum adiabatic temperature rise. That is the maximum temperature rise that you can expect if you are carrying out an adiabatic operation. Theta r is the dimensionless cooling temperature or coolant temperature, and an interesting parameter psi, which is called as Semenov number, and if you look at these terms in this actually is a ratio of heat release potential to heat removal potential. Why do we say that? Because if you actually look at, let's write down this in form. If you look at this psi parameter, for example, this term is the maximum rate of reaction multiplied by heat of reaction. So, that is a heat release potential, and if you look at the remaining term, it is actually, one can look at it as U into T naught divided by 4 by dt, which is actually nothing but, if you look at this heat removal term. Now, what is the maximum potential, or is a measure of heat removal potential? 4 u T naught by dt, and that gamma is because we have non-dimensionalized it in a particular way. But the point is that this parameter psi measures heat release or rates heat release with vis-a-vis heat removal. So, what does a large value of psi, what would it mean? Large value of psi would mean that heat release potential is much higher than heat removal potential. Okay. Now, let us go back to this equation, mass and energy balance, and in order to simplify this analysis, we are going to make one assumption which is not strictly valid when the reaction is taking place, but is a good approximation, because we find that this heat hotspot or these kind of behaviors are occurring very early in the reaction. What do I mean by that? If you go back and look at our example of this reactor, our hotspot is definitely at the early stage when the even before the midway point. So, what we are going to say is that in order to look at least qualitatively what behavior we can expect, we are going to neglect these conversion phenomena or reaction, or we are going to assume that x is very small. That means, not much reaction has occurred. If that is the case, then I can write my energy balance, the same energy balance. So, I am going to rewrite this energy balance by neglecting this 1 minus x term, because that value is close to unity. So, that is why I said this is not an exact analysis, but it is a good approximation. So, what we are going to say is that my energy balance is of this kind: d theta d tau 1 over b as e raised to theta by 1 plus theta by gamma minus 1 over psi theta minus theta r. That is, all I have done is in this particular equation, in this particular equation, I have neglected x. I have assumed it to be a very small value. So, if we like, we can keep b on this side, or if we do not like it at this point, let us bring b over here. Okay. Now, if we see that since our theta behavior is gone, I can now look at this behavior of this system. Since our x is gone, we can look at by simply looking at this theta equation. Okay. So, I have taken x to be very small value. Okay. So, once again, this, what is this term? This is heat generation term. So, Qg, and what is this term? Heat removal term. So, Qr. And for sake of simplicity, I mean just to make things little more simpler, I am just going to take b on one side, because it is common in both these factors, and we are just going to say this is Qg minus Qr divided by b, but if I express Qg as just e raised to theta by 1 plus theta by gamma, I am still okay. Okay. So, what is this energy balance trying to tell us? It is trying to tell us what we expect actually, that change in temperature along the length of the reactor will be a result of imbalance between the heat generation and heat removal. That is what we expect. So, if heat generation is more than heat removal, we can expect increase in temperature. If heat generation is less than heat removal, we can expect the lowering of temperatures along the length of the reaction. Now, let us try to graphically see how these two terms depend on the temperature. So, if we look at this Qg term, which we have said that this is just theta by 1 plus theta by gamma, what happens to this Qg term when theta is 0, that is where temperature is at the inlet condition, Qg is 1, right, because it is only function of theta. And when theta becomes very large, goes to infinity, let us say, I mean in reality we will never go to infinity, this will be e raised to gamma. So, Qg goes to e raised to gamma. So, some kind of a saturation. And what about Qr? If you look at Qr, which is 1 over psi theta minus theta r. So, QR is also a function of dimensionless temperature theta, and we can see how it changes with theta. The relationship is linear with the slope 1 over psi. So, now let us try to look at graphically how these two functions look like. What we are seeing here, is temperature theta on x axis and the function qg, which was e raised to theta by 1 plus theta by gamma, which is shown by this red line over here. Okay. And function QR which is 1 over psi theta minus theta r graphically will look like straight lines, which are these different lines that we see with the slope 1 over psi. So, there are various these different lines, but slope of this line is 1 over psi. Okay. Now, and what is our energy balance? Our energy balance is Qg minus Qr. Okay. So, on the y axis we have two different types of heat rates, one generation rate and one removal rate. Generation rate showed by red line with we saw earlier that this limit is e raised to gamma and value is 1 when theta is 0. So, now let us consider a situation where we have psi value very small. That means, slope of this line, straight line for heat removal rate to be very large, and this is what this curve which shown as number 2 over here indicates. Okay. Now, what does this particular value of psi indicate? So, what we have at point 2, our psi value is small. What does it mean? It means that our heat generation rate is much smaller than heat removal rate. So, now let us try to imagine how this reactor behavior will take place if our temperature is as we proceed along the length of the reactor. We start with theta equal to 0, theta is 0 at the inlet. So, we start over here and we see that Qg is higher than Qr. So, temperature will start increasing. So, I am just going to plot a simple sketch here just to illustrate the idea that how temperature will increase. But what happens as my temperature is increasing? I think I need to just enlarge that figure so that we are together on this. So, this is my heat line, removal line, and this won't help either. Let me make it even more bigger. So, this is my heat removal line and heat generation line, and let me show my heat removal line, that this line 2 is at least little bigger. So, we started our operation somewhere over here, and we see that heat generation is more than heat removal, and so temperature will slightly increase. But what is happening as temperature is increasing? Temperature increase means what? We are moving in this direction. As temperature is increasing, the generation rate gap and the removal rate gap, that is this gap, is narrowing down. That means what? As we are proceeding, as the reaction is proceeding in the reactor, the rate of increase in temperature is going to go down, because generation rate and removal rate is gap is lowering. That means this two difference is lowering, so temperature increase will lower, and it will keep on lowering, or in other words, temperature will never exceed this particular value, whatever that value, theta m. So, temperature will always remain below that particular value. In other words, the temperature we will have a safe operation, right, because temperatures won't rise. Now, let us consider an operating line such as 4, where psi value is large and the slope is small. Okay. Slope is small. So, let me try to use the same logic, and without going into too much details, let us try to see what will happen in the reactor, and let me just enlarge this figure for this case also. Okay. So, this is our heat generation curve, and for sake of argument, let us say my heat removal curve is something like this. Okay. So, let's see now how our temperatures will vary. We start over here, we see that the gap is large, so temperature will start increasing. So, as the reaction proceeds, this is theta and this is Qg and this is Qr, removal rate. So, what is happening as our temperature is increasing, because this is my theta equal to 0 and then temperature started increasing, it appears that this gap is narrowing down, but we see that there is always a positive difference between heat generation and heat removal. What it would mean? It would mean that if you look at this energy balance, Qg is always greater than Qr. That means this temperature will always keep rising. Temperature will always keep rising. Something very similar to what we saw when the hot spot occurs. That is, if our parameter value psi is very small, we have a safe operation as shown over here. But if psi value is large, that means heat generation potential is much larger than heat removal potential, then what we see in principle is that the temperature will always keep on increasing. What about psi values intermediate? We see that for the Semenov numbers which are intermediate, we see that for some values such as 3, we can have 3 different values of intersection points, and this one over 5 here and 6 here. What are these two lines? These two lines are actually tangent, the straight lines which are tangent to this curve. They have their own significance, and they in turn determine the critical parameter ranges that we talked about when we had this sensitive and insensitive regions. We will stop here for today and continue this discussion in the next session, where we will see how we determine those critical operating conditions and what happens actually when the reaction is also taking place, because this is all discussion based on no reaction taking place. So, that is the topic that we will start with in the next session. Thank you.